Okay, so hello everyone, welcome to today's reading group. So today I'm going to cover two topics in Erickson's course. The first topic is about spectral knurling for graphical models. Essentially, we are going to know an efficient parameter knurling way compared to EM algorithm, which is faster and is local minima free. And the second topic we are going to briefly introduce is that currently we are more focused on the large scale training of our algorithm. So I will take a very brief introduction to some parallelization techniques used in some optimization algorithm and the MCMC algorithms to facilitate the fast training of our models. Okay, so let's first start with spectral learning for graphical models. So far, I think we've gone through many latent variable models, such as hidden Markov model, and our key focus is how to learn such model, right? And we are all very familiar with one technique that is used for learning the parameters, which is the EM algorithm. So the EM algorithm will iterate between the estimation step and the learning step. So basically, in the E step, we try to estimate the assignment for each of these latent variables. And so basically, because in this, for example, in this HMM model, we usually only observe the value for these observed variables, but we have no idea what is the assignment for these latent variables. So that's why we will utilize this EM algorithm to learn these parameters. So in the E step, we try to estimate the assignment for each of these latent variables. And in the M step, we treat them as lower values, observed variables, and then try to maximize the joint likelihood. However, EM algorithm would have several drawbacks. One of that is it is relatively slow because it's kind of an iterative algorithm, and secondly, it may be tracked into the local minimum. This is because the latent variable model that we've learned so far are not always convex. And the way for EM algorithm to alleviate such local minimum is to have for example, multiple random initialization, maybe for example 100, but such approach will further end up the slowness of EM algorithm and make it even more expensive. So spectral learning is a very interesting idea, and it is a completely different paradigm of learning in latent variable models, and it is totally based on linear algebra. So it will have very nice theoretical properties. So it is provable, consistent, and it can offer deeper insight into the identifiability, which we will talk about it later. Also, very interestingly, in practice, the spectral learning is local minimum free. Why is that? Because later on we will show that the spectral learning will not incorporate any latent variable, meaning that although the modeling part contains the latent variable, for example, h here, but during the parameter learning stage, we will not try to infer the value for each of these h. We will use a smart way by using the linear algebra so that the joint probability is totally represented by the observed variables. So the computation will get rid of all these hidden variables. So it will be local minima free. And as of now, it has been tested on many different latent variable models, and the results show that it can achieve comparable performance to EM algorithm to the downstream task while having a 10 times to 100 times speed up. So it's relatively efficient. And also it can model the non-Gaussian continuous data using kernels, which usually performs much better than EM in this case. But in today's lecture, we're just looking at the example we're just doing with discrete data. because that's more convenient for us to understand its mechanism. Okay, so let's firstly see what's intuition behind spectral learning for latent variable models. So in many applications, the use of latent variable models, the end task is not to recover the latent states, which is the value for this edge, but instead our goal is to use a model for prediction among observed variables. For example, if it is a dynamical system, we observed some trajectories in the past and then want to make predictions in the future. That's our ultimate goal. And these latent variables are just vehicles that drives us to lead to the predicted values for these observed variables. So basically, about 10 years ago, that's the time when spectral learning is most popular. So at that time, people start to think that, okay, since if we do not care about the value of latent variables, is there any way we can get rid of it? Actually, we can by using the spectral learning, but a very naive way is just what if we just get rid of all these hidden variables? That will not work in this case because that will make all the observed variable becoming a clique so that each of them are dependent of each other. So that's basically not what we want, because the reason we use this H&M model is trying to build some conditional dependency among the data for more efficient inference. So if we just like very roughly integrate them out, it's kind of, we get rid of all these assumptions. So that's not what we really want. We still want that dependency. So essentially, here is a way to help us look at it. So assume we have 3 observed variables with cardinality n, and we have 1 latent variable h with cardinality k. So if we think about, now let's try to play with the cardinality k to see what will the graphical model changes along the changes with k. So in the very beginning, let's try to think about if this k equals to 1, what will this graphical model represent? So very interestingly, if this h only has 1 state, this graphic model actually means that all the 3 variables are independent. So how can we understand it? Because intuitively, h only has 1 state. So no matter how we changes the values of x1, x2, x3, h will always be the same value. So therefore, there's no hidden driven force which can be used to impact the 3 random variables in any way different. And mathematically, we can also try to write down here. So essentially, we can try to write down the joint probability of observing x as the multiplication of the conditional probability over the summation of h value. But however, now h only has 1 value, which is h0, so the summation is get rid of. And once this h only has one value, which is h0, so the probability of x1 conditioned on h0 is equivalent to the probability of x1 itself. So essentially, when the cardinality of the hidden variable is 1, that means it only has 1 state, then these 3 variables are actually independent. So let's see that now the observed variable each has.
Actually, I really need your help to help me to understand the motivation here. So the reason that we need this graphical model is like we are able to, based on this structure and do the decomposition, right? Then we can write down this joint probability. And right now, when you try to like get rid of this latent variable, so what's our goal here? Are we interested in compute this marginal distribution? So what's our goal here?
Okay, so for the remaining material, we are interested in learning the joint. In learning the joint probability of this x, which is a which is a big tensor, right?
There's a joint probability of x1, x2, and x3.
Yes.
Okay. So we're interested in joint distribution over the three variables. Okay.
Yes. Okay. Yeah, sorry I didn't make it very clear in the very beginning, but yeah, so in what we are doing in the following, we're trying to find a way that we do not incorporate this hidden variable, but we are able to estimate this joint probability with the consideration of the dependency among these variables. So that's what our ultimate goal. But we'll start with the illustration here. So firstly, if this edge only has one state, we see that, okay, it illustrates that all these variables are kind of independent. But
here, there are two different things here. So I want to make sure. So first of all, here we only have one latent variable, right?
Yes.
Do you further assume that latent variable can only take one single value?
Yes, so it's only have one state.
Okay.
Okay. Yeah. So that's the case when edge only can take one value, meaning it only have one state. So let's see when we change in another extreme cases. So let's see each of these observed variable has m states. And then if this edge has m to the power of 3 states, then the latent model can be exactly equivalent to a clique, because if you considered when we constructed the conditional probability table based on this edge. So essentially, if this edge would have this number of states, then we would have this number of parameters to construct this conditional probability table, and that will implies. So that is the number of parameters we need to describe that. Okay, these x1, x2, x3 are kind of all dependent of each other without the assumption that they are existing any like conditional dependency here. So essentially what we are trying to do here is to show you that we are going to trying to connect the level of dependency of these variables to the number to the cardinality of the edge, which is the number of values edge can take. So
can you elaborate why the CPT has M3? I mean, if there are M states, why we need this?
This means
M3,
that
M cubic.
Okay, so that means that because each of these three can take m values, so essentially there are how many combinations of them is just m cubic, right? So essentially, if edge has m cubic states, meaning that each of these configuration of x1, x2, x3 will have a unique edge here.
So edge has m states, right? For x1, x2, x3, we didn't discuss about the states.
Yeah, sorry, here. So x1, x2, x3 is assumed to have m states. So the extreme case is that edge has m cubic states. So that will imply that actually imply this graphic model here.
Okay, so m is for the observed variables. Okay.
Yes. Okay. So essentially, we see that actually when we change the cardinality of this edge, it will result in different graphic model in this very toy example. However, under existing methods, latent models all require EM to null regardless of the number of hidden states. But the spectral nulling is trying to answer the following question. Is there a formulation of a latent variable models where the difficulty of nulling is a function of a number of latent states? Because we already see that the number of latent states can kind of reveal the level of dependency among these variables. So this is what the spectral view will answer. It will try to explore the relationship between the matrix rank and the independence. Where we talk about the matrix rank, it's just the joint probability, this px. So later on, we were just doing some linear algebra on this joint probability x with its rank, and we can see that, okay, this rank will kind of reveal the dependency among these variables. Okay, so before we move to the spectral view, we need to briefly mention some linear algebra that correspond to the probabilistic operations that we used before. One rule is called the sum rule, which corresponds to the marginalization of a joint probability. So we use the following like linear algebra to express this, which is quite like straightforward. And the second is called the chain rule, which is how you get the joint, right? So by just multiplying the conditionals. And the equivalent algebra expression is as follows. Remember here, this y's value is just at the diagonal, which is to keep y from being marginalized out. So now let's look at the like spectral or algebra view of the graphic model. Assume that Assume that each of these variable would have m states each. So if we look at their joint probability matrix, this matrix would be m by n. So if we do not know any kind of dependency information among these two variables, then this matrix can be of any configuration, right? But what if we know that if A and B are independent? So if A and B are independent, the joint probability matrix will be rank 1, because if we look at each row of this joint probability, it's just that the A taking one of the value and B taking all the other values. So essentially, all the other rows are just multiples of one another. So the rank of this joint probability matrix is just 1. And also we know that also from our previous discussion, if this of course if this m by n matrix has rank n, so it corresponds to like kind of these two like variables are like fully dependent of each other. But we know that for this m by n matrix, its rank can be within rank between rank 1 and rank n. So once we observed a joint probability matrix where its rank is between 1 and n, what does it really refers to? Meaning that what's the corresponding graphic model that we are talking about? So if the rank is between 1 and m, then A and B are not marginally independent. So they are only conditional independent given a hidden variable x. So essentially, if this joint probability matrix AB is of rank k, we can represent it using this graphic model where we introduce a latent variable x, and this x has k states, where this AB have m states. Because we can kind of, based on this assumption, trying to factorize this whole matrix using this matrix multiplication. So essentially, we know that if the rank of the multiplication of these three matrices would be smaller or equal to the smallest rank among all of these metrics. And if we look at this factorized matrix, we can see that, okay, this PA given X, PAX, B given X, they are at most of rank K, because X only will take K states. So essentially, so the spectral view of the graphic model is that we're trying to use, we're trying to use the cardinality of the hidden variable to reflect the rank of the joint probability. So by changing the cardinality of the hidden variable, we allow different degrees of dependencies between the observed variables. And this will make the learning process very convenient and easy, because we can try to, for example, we in all our for example, for our HMN model, in order to know that, we will know in advance that how many hidden states we have in H, right? So that is kind of by design. So essentially, using this knowledge in the spectral view, we are trying to factorize this PAB into a rank K matrix where this K is the number of hidden states that we have. And the way we're going to use a factorization is to use this linear algebra because now we're playing with matrix. So we can utilize the tools we are very familiar with, like the rank, eigenvalues, SVD, and tensors. So, uh, so last example is just a two variable example. So here we can look at a more interesting example to illustrate how we are going to do the matrix manipulation to factorize this joint probability into exactly a K rank uh, 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 by by saying that this is a K rank K matrix, how we are going to factorize it only use the observed variable. So that's what we are going to solve now. So now let's look at the more interesting example where we have four observed variables. Each of them is associated with m states, and also we have four hidden variables, and each of them are associated with the same k states. Okay, so again, we can construct a condition, joint probability matrix in the 2D space where the matrix is m squared by m squared, and where the row is indexed by the value of variable 1 and variable 2, and the columns is indexed by the value of variable 3 and variable 4. And now let's see that it has rank k because now we have this k hidden states. And essentially, we can actually do trying to if we know the rank is k, actually by using the standard matrix factorization approach, we can easily find an L matrix, which is m by k, and R matrix, which is k by n, so that we're trying to represent this m with a smaller matrices. The idea, the interesting thing that such factorization is not unique. Actually, we can find another factorization by introducing a hidden states variable h2. So essentially, we can represent this joint probability by assuming that this joint probability is conditioned by this hidden variable h2, well, the value of x1 and x2 is based on is conditioned on the value of h2, and also the value of x3 and x4 is also conditioned on h2. So essentially in this way, we are kind of factorize these four variable matrices into a multiplication of smaller matrices. But still, this factorization, right, we still have these hidden variables. So for example, if we want to know the values for this joint probability, we still need to compute the values for each of these matrices. That's not what we want. So the interesting thing.
I have a question here. So, but for the matrix multiplication, there's no constraints. But if you want to have this probability interpretation, then for each entry, we, for example, in M, right? So then we are saying, oh, each entry has to be a value between 0 and 1. And if we sum up all of them together, because it's joint distribution, then it has to be 1, right? And then if we do this factorization here, like if we interpret as a conditional probability, then similarly, we have to satisfy all those constraints. But in general, for matrix factorization, right? So we don't have that constraint at all. We just wonder, I mean, conceptual-wise, I think they are indeed related, but when coming to this concrete technique issue, right? So it seems to me they are not that exactly equivalent.
Are you saying by looking at because for example you look at the right hand side, you are saying that by utilizing the right hand side to compute this joint probability, maybe this matrix will not satisfy that the sum of each row equals to 1.
If right hand side everything is like satisfy all those constraints, everything is probability, then left hand has to be probability. I just wonder, like when we apply this matrix factorization technique, then there's no guarantee that L and R, right? So they satisfy these constraints. But then if we use that to compute M, then also it does not have to satisfy the probabilistic constraints. I just wonder how they can solve this problem.
Okay, so yeah, so that's a very interesting question, because later on we will show that we will find a unique or not unique but a very special like factorization of this m by using only kind of the observed variables x. So essentially the right hand side factorized like matrices, they are all they will all be probabilistic matrices which will satisfy such constraints, and we will
Okay,
see.
interesting. So okay, let's see how the constraint can be put into the optimization.
Okay, so essentially we see that here what I want to illustrate that because m can become decomposed into m equals lr, and we can equivalently write it as by this joint probability equals this multiplication of these three matrices. And for example, we can view the first two multiplication as L and the last one as R. However, now there still contains this H here, right? So that's actually what we want. But the interesting thing here is that such matrix factorization is not unique. For example, once you find an L and R, you can plug in an S multiplied by S inverse. So essentially, they will give you the same left-hand side matrices. And the key idea of spectral knurling is that by choosing some appropriate S, it can lead you to do a factorization of this big M by using only the matrices that includes the observed variables X. So essentially, the ultimate goal is trying to find such as so that the left-hand side, the factors will only contains all these x. So using this example, we can easily find one solution here. So let's see, we only want to factorize this matrix of these four variables such that it is a product of matrices that contain at most three observed variables. For example, we want to have one factor which is this and another factor which is this. Okay, and if we look at these two factors, we can try, because they are containing three variables, we can further follow in the same manner to introduce a hidden variable so that it can be decomposed into smaller factors that comprise of just x1, x2, h2, or x3. And we can do the same thing for the second factor. And the interesting thing is that once we take the product of these two terms, okay, and now together we have 6 terms in total to do the multiplication. The multiplication of the green terms will result in the p x1 to x3 4, which is our big M here. And the red product of the red terms, essentially it will give us p x2 x3. So what does this mean is that we find another alternative factorization where we factorize this joint probability as a multiplication of these two factors multiplied by the inverse of this one, right? So in this way, we kind of find an alternative factorization for this joint probability. And the advantage is that factors are only functions of the observed variables and can be directly computed from data without this EM. For example, if we want to compute these matrices, all we need to do is just to do the counting, right? To count how many times for example, for a special assignment, the occurrence in this data set. But the caveat is that some factors are no longer probability tables. For example, this inverse one, right? Because this px2, x3 is essentially probabilistic matrices, but once we take the inverse, it can sometimes become negative. We will later talk about how we're going to deal with this. But overall, so from all the way down here, we now find of an alternative factorization which has factorized this p into where all these factors only contains observable factors. So we call this observable factorization. And in such way, we kind of get rid of this hidden variable h here. Okay, and another thing to mention that such factorization is not unique because we can find factors 1, 2, 3, 2, 3, 4, and we can also find the other kind of factorization following the same manner. And what we usually do is that we would do better empirically if you could combine both factorizations. So essentially, the normal way to do that is trying to take the expectation over different such factorizations to estimate this p. Uh, so now let's try to again to enhance the like relationship between such factorization to the original factorization where we have the latent variables. So essentially, why we have derived this one is that we're starting from this very obvious factorization, and our idea is trying to find an s so that okay, this m will remain the same by plugging this s multiplied by s inverse. So by setting this s as p x3 condition on h2, actually we are able to successfully convert this one into what we have found so far. So essentially, that's basically the kind of key idea of the spectral learning, meaning that, okay, although we still have such dependency assumption introduced by the modeling part where we have the hidden variable, but by doing such factorization smartly, we're able to find an alternative way that such factorization only have factors that contains the observed variables. And for now, you may not find that it is very kind of powerful because now that we only kind of get rid of this edge, but on the left hand right hand side, the matrix size is still of 3 variables. The original one is 4 variables. It's still statistically inefficient, right? So, but this will be more powerful if we take into more kind of variables on the left hand side. Because what is cool here is that if for every factor on the left hand side, if the number of variables is more than 3, we can always further decompose it into smaller factors that are of size 3. So in the final, the right hand side would only contain factors that are of functions of observed variables, and these factors are of size 3. So here's an example. If now we consider the HMM with 5 observations, then using the same arguments as before, we can firstly factorize it into these 3 components, where the first one contains 3 variable, the second one contains 2 variable, and the last one contains 4 variable. But what we can do next is to further decompose the third one. So following the same trick, we previously already showed that how we are going to factorize this 4 variable joint probability. So we can further decompose it into the same way and plug it back. So finally, this joint probability of 5 variables will be multiplications with matrices that only contains maximum of 3 variables. So if you compare the time for computing, right? So essentially to analyze the statistic, meaning that doing the count for the matrices of size 3 compared doing the counting for the matrices of size like n by n, this is much more efficient for this computation. Okay, so based on this factorization, actually our training and testing are very like easy. So suppose we have decomposed our joint probability like this. So in the training, what we really need to do is just to try to estimate the maximum likelihood of all these 3 factors, right? So for example, to estimate the maximum likelihood of the first factor, we only need to do the just to do the counting from the data. So we can easily construct these matrices. And similarly, we can also do the counting for the second factor and take the inverse, and for the third factor. So essentially the number of counts we need to do is much smaller, right? Because if you want to directly estimate the counts here, it's just a very all of the entries you need to count its statistic value. But here you only need to count the statistic values of these smaller matrices. And this factorization also uh, preserve such dependency among these variables. And this is the only thing we need to do in the training time. So it is not like EM algorithm. We need to firstly estimate the values for the hidden variables and then to plug in the values for the hidden variables to maximize the likelihood. But we only need to do the count for the observed variables, which is quite convenient. And in the test time, what we only need to do is to just plug in look at the corresponding entry for the specific value of x1, x2, x3, x4. So then we can get the estimated probability here. And here's some analysis regarding kind of the consistency and efficiency of this approach.
I have one question.
Okay.
So this factorization is valid only if it is underlying model structure is a hidden Markov model, or is it general conclusion?
Actually, such factorization should be different when you apply to different hidden latent variable models, right? Because the dependency of different variables illustrated by the latent variable models are different, right?
Right. So like the conclusion that we derived here, this simplification is possible because we made that assumption that there is that sequence of hidden variables and x1 and x2, x3s are all dependent on the individual hidden variable.
So you're saying that maybe change to another latent variables such we can no longer decompose it into such smaller factors?
My question, I guess my question is, what are the assumptions that we are making here so that guarantees this kind of factorization?
Mm-hmm.
When can you always factorize this way?
Okay, so if you look at the way we're doing the factorization, for example, here, the way we're doing factorization, here we kind of incorporate this hidden variable h2. Why we kind of write down this decomposition? This is directly from the latent variable model that we are using, right? For example, HMM, we can assume that this x1, 2 can be conditioned on this second hidden variable, and so does the x3. But if you change to a different latent variable, maybe the structure here can be different. But the conclusion is that once this factor has so many different variables, we can always follow kind of the latent variable structure itself to further decompose it, that the factor only will contain maximum 3 variables. This is the same for all the latent variable models.
But I'm a little bit confused about that conclusion because our original model without any restriction, the original model is if there are in this particular case, there are four variables, right? Then there is potentially m to the 4 parameter space that we are working in.
Yes.
Or maybe n minus 1 to the 4, but without that. And but on the right-hand side, the number of parameters that we have is m to the 3 plus m to the 3 plus m to the 2.
Yes.
So you can never go to m to the 4. So I'm not convinced that this is always possible. There must be some conditions that we are assuming that allows this kind of simplification.
So you see, there might be possible that the parameters in the right-hand side may be larger than the parameters on the left-hand side.
Why is it so?
I mean, is that what you see?
On the right-hand side, the degree of freedom that you have is m to the 3 plus m to the 3 plus m to the 2. So
Yes.
it can never be m to the 4 degree. So the degree of freedom on the right-hand side is m to the 3, and degree of freedom on the left-hand side is m to the 4. And in some sense, if this particular factorization is always possible, the claim is that any model that has m to the 4 degree of freedom can always be simplified into m to the 3 degree of freedom, which I cannot believe it.
Oh, I see. Let's think about in this way. So the reason why we are able to kind of defactorize it in these smaller factors is that we kind of make every latent variable model, right? They will assume that many dependency among these like different variables. So if no such dependency exists, then all we can do is just to like estimate the m's it's just to estimate all the parameters on the left hand side without making any like simplification. But even though different latent variable models, they have different structures, but in some degree, they will kind of assume such model like variable dependency. So that's why we can decrease the number of variables we need to estimate here.
So I think my question is, when is this simplification possible? What is the assumption that we are making here that make these kinds of factorization possible? I think that is my question.
I see. So the assumption we made here is that for every, for example, for all of these 4 variables, we can introduce a hidden variable h, where based on this h, then part of these variables are conditional, independent of each other. For example, here we assume given this h2, then this x1, x2 are conditional independent of x3. So we always assume that in different latent variables, we can always find such split that given a hidden variable h here, then two groups of the variables can be conditional dependent of each other. So we can further decompose it into the smaller factors.
Well, you see that kind of assumption, hidden variable, because of I can increase the cardinality of H2 to whatever number that I need. That we are not making any assumption in some case.
You mean when the number of h, for example, is greater than the states of the observed variable?
Right. If H2, if this is something that you did much earlier, if you assume that H2 has the cardinality of H2 is m to the 3, then we are essentially making a click. We are not making any independent assumption at all.
Yes, so actually we are going to talk about, I think I didn't mention it here, so it will cause some confusion. So later on we will talk about that, what problem will cause if the cardinality of this h is kind of growing big compared to the cardinality of this x. So there's some thing we need to deal with that, and we will see a concrete example when these cases happen and what problem it will cause.
I'm still very uncertain about. So I think at the end of my question really boils down to that question: when can this deep factorization? When can you do this factorization? When is it possible? And I'm pretty sure it's not all the time. There must be some conditions that needs to be met in order to do that factorization, but I'm not clear about exactly what that condition is.
I see. So, right. Okay. So from the based on my reading for this lecture, the condition that this one can be factorized in this way is when this H2's cardinality K is smaller than this cardinality of X. Once this H2's cardinality K is greater than this M, we will have problems. So we have special tricks to deal with that, because in that way, this factorization will no longer exist.
Oh, you are saying that this factorization is not possible when H2's dimension is larger than, let's say, M?
Yeah, so this K is greater than M.
Okay.
Okay. Yeah, I think basically that's a very like good questions for us to discuss, because I myself is also the first time learning it, and I found that later on I think very quick we'll have a discussion about the relationship of K and M, and how we are going to deal with that. So
I want to clarify that, since like for this one, to try to provide a new way to do the learning, right? So, yes. So when we do the factorization, we need to assume this graphical model is given. Is that the assumption here?
Yes, otherwise there's no any dependency assumption exists.
Okay, so the factorization is going to be guided by this graphical model, because yes. Like in your case, right, in Markov chain case, is it, okay, this is a hidden Markov model.
Yes.
So then this kind of factorization is valid. So that's why we can do this kind of matrix factorization. Okay, so if it's like a hidden Markov random field, then this will be completely different.
Yeah, so one drawback for this spectral knurling compared to EM is that for EM, it is very easy to adaptive to different latent variable models. But for this spectral knurling approach, when you're trying to adapt to different latent variable models, the factorization or the matrix trick you need to play with is quite different, and you need to decide by yourself.
I see. Okay.
Okay. Okay, so let me go back to where we are before. So based on this kind of factorization, where we smartly get rid of this hidden variable h, in the training, all we need to do is just to compute the maximum likelihood of these factors, which is much smaller, right? And in the test time, we just plug in the corresponding value we want to evaluate, so we can get its probability. And here's some analysis towards its consistency. So if we do not want to make any conditional dependency assumptions, then, or essentially we do not want to build any structure among these latent variables. All we want to do is trying to count, okay, the co-occurrence of each of these entries in this big gigantic table. But this kind of maximum likelihood estimation will only be approaching the true probability when we have many available data. So while this one is consistent, it is not very statistically efficient. By saying statistical efficient, meaning that compared to another model to estimate the true joint probability, this method would require more data in order to get the same accuracy. So directly estimated from the data without any dependency or structure assumption, it is not statistically efficient. And what EM is doing is trying to introduce this hidden variable h, and iteratively trying to infer the values of h, and then infer the values of the observed variables x. But this will get stuck in the local optimal, because now this MLE is not directly computed over this observed variable, because the way we computed the MLE from observed variable is just looking at the real data, the count. But now this count now just becomes kind of the depends on in the current iteration what your inferred H2 looks like. So essentially, there's no guarantee that the obtained MLE uh, 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 it is not guaranteed that this maximum likelihood estimation will approach the true distribution. So there's no theoretical guarantee. But in this spectral knowledge, we provide a third way to estimate the joint probability matrix. So essentially, we're trying to do the MOE for each of these factors. But different from EM, in this case, all these factors only contains the observed variables. So in this way, this is and such MOE can be directly computed or count from the data itself. So in this way, this is consistent and computationally trackable, but at some loss of statistic efficiency due to the dependence on the inverse. So essentially, it also requires uh, a relatively amount of data. Otherwise, the inverse will not exist, right? Because if you think about this, data is relatively sparse, so many of these matrices entry would be zero. So in this way, this inverse will just do not exist anymore. So essentially, regarding the statistical efficiency, in order to get uh, uh, close to this true distribution, it still requires some amount of data, maybe more amount of data compared to EM algorithm. So now let's talk about the problem that we are discussing about. So essentially, the standing point for talking about that is different from Professor Cho has raised, but I think they are talking about the same question. So if we look at this factorization, actually there's a term which is the inverse. So here's a natural question arising, when will this inverse exist? So if we look at the factorization for this joint probability of x2, x3, right? So in order for this to be able to do the inverse, it must be full rank, meaning that all the right-hand side matrices also need to be full rank. So actually this is in general a requirement of spectral knowing, although it can be somewhat relaxed. So if the case is that the number of states in the observed variable, which is m, is greater than the number of states of the hidden variable k, how shall we deal with this kind of inverse? Because essentially now it will this because essentially if this m is greater than k, the inverse will not exist. But this situation is easily to be fixed. We can just utilize the dimensional reduction technique. For example, we are trying to select the top left and right key signal vectors of the joint distribution here, which is u and v, and then we're trying to multiply it in this way, and then this kind of will generate as a k by k matrices instead of m by m, and then we can take the inverse, and finally we just multiply back this u and v and ut. So you can very easily verify that if you multiplied this part with the original p x2 x3, they will give you the identity matrix. So actually this dimensional reduction can help us to deal with the issue where this m is greater than k. But the question would be very hard to solve if the k is greater than m, especially not greater than m. And intuitively, this seems very, very strange, right? Because why would have the number of states greater than the number of observed variables states? So here's an example to illustrate a situation that we encountered. So intuitively, we see that if we have a large k, which is a number of states for the hidden variable, and a small m, it means that all the variables kind of have a very, very long range dependencies. So let's consider a scenario like this. So here we want to generate a sequence. The generation process looks like this. So firstly, we have a symbol which can take value either of x or y. So it have 0.5 probability to take the value of x and 0.5 probability to take the value of y. And once we decide the value of S, we now start to generate the sequences. We will firstly print A n times, and then we print S, and then we print A n times, and then print S, etc. For example, when n equals to 1, the sequence we generate can be either AX, 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 or AY, 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 because we only repeat step 2 and step 3. And when n equals to 2, what we will generate would be AAX, AAX, or AAY, AAY, etc. So in this case, if I look at what's the number of m and k, actually this will result some cases k is greater than m. Why is that? Because the sequences we can directly tell the number of the cardinality of the observed variable can be either a, x, or y, right? So essentially m would equals to 3. But the number of hidden states now would equals to 2n. Why is that? Because we now will no longer only remember what is the current kind of the value at this observed variable, but we also need to remember what to produce for the symbol x and y, and also how many times a is produced. For example, if we look at this a and this a, actually their hidden states are different, because standing at this a, this hidden like track variable may tell you that, okay, now we only print this a 1 times. And standing at this a, right, it says that, okay, now I print a, but this state will also tell me that previously I have already print 1a. So essentially, if this s only equals to x, we will have these n different hidden states. But if this s equals to y, we'll have another n different states. So essentially together we'll have 2n hidden states for the hidden variables. So in this way, we will interpret it that it is no longer a first order hidden Markov, but now they are trying to capture such long-term dependencies along the sequences. So essentially, from the intuition way that from the factorization part, we see that once this n is greater than this, k is greater than this m, the original factorization will no longer exist. But we still want to, under these circumstances, estimate the joint probability. So the trick we are using is trying to, instead of using the values of the hidden variable as a key to curate the joint probability, we now are trying to represent each of the observed variable using its long-range features. For example, starting at this variable x2, we can represent it as all the as a vector, where this vector kind of reflects left-hand side sequences. And how long these sequences would be and what information these sequences would contain is by design. For example, in our previous example, we can kind of decide this left-hand side feature vector as how many times this A has, for example, appeared. And similarly, for this x3, we can use the right-hand side vector, a feature vector, to represent its current like state. So essentially, again, it can be how many times A appeared, and also the window size can vary. So in this way, because previously what we are not able to deal with is that the inverse of this will no longer exist when this k is greater than m. But now when we replace this original x2, x3, because previously they are just the value of them to represent its state. But now we are going to use the feature vector to represent its state. So essentially, you can see the number of states for this x2 and x3 is kind of increased by using this feature vector, right? So in some sense, we have already increased the cardinality of m so that it will be greater or equal to this k. So in this way, we can again trying to do the inverse just by plugging the original x2 using this phi L and the original x3 by using this phi R. So that's how we deal with the cases if the number of k is greater than the number of n. So is this part clear?
It's fine for me.
Okay, so yeah, so essentially, yeah, I think the previous question you asked is related to this because from the equation itself, when the k is greater than m, actually it will no longer exist. And the way we deal with it is to somewhat incorporate this feature vector. And this feature vector is kind of to some degree increase the cardinality of the observed variable states itself. And let's look at some very interesting experiment results here. So here is one paper because, as I said, the majority of the development of the spectral learning is about 10 years ago. Recently, there may be some follow-up, but the most popular period is about 10 years ago. So here's a paper from 2012. So essentially, it shows the comparison on a synthetic third order HMN example. So it shows a runtime comparison and error comparison among three algorithm. The blue one is a spectrum, and the red one is an EM algorithm we are very familiar with, and the green one is an online EM algorithm. The online EM algorithm is that because the traditional EM algorithm requires the whole data to be available at each iteration in order to compute the maximum likelihood, right? The online EM algorithm will try to update the parameters in an online fashion, meaning that after observing each new data, it will try to update its parameter. Instead of in the very beginning at every iteration, it will have the whole data stored in like the disk. So it will do these online approaches. So we can see that by comparison among these three approaches, the running time of spectral learning is relatively small, and especially the differences between the gap will increase when the training samples increases, right? And the second graph shows that the kind of the evaluation error, which is a estimated joint probability matrix versus the ground truth probability matrix. So essentially, we can see that the spectral learning can achieve comparative results to EM algorithm, but combining with the first figure, its speed is much faster. And the results for other structures in this paper they reported looks similar. Okay, so that's basically the comparison of the spectral learning to original traditional EM algorithm. Okay, so any questions? Okay, so essentially that's basically the whole lecture part about the spectral learning. So if we want to make some summary, the key idea of spectral learning is that we want to learn the joint probability matrix for these latent variable models. But these latent variable models traditional way is to use this EM algorithm, where this EM algorithm will try to infer the values for the hidden variable h first and then utilize as this h value to maximize the joint probability of the observed variable. But in real problem, we are usually not care about what the value of h really means. So that inspires people to invent another approach called spectral learning. They trying to directly estimate the joint probability by only utilize the observed variable. And the way to achieve it is by utilize the matrix. The way they do it is kind of can be viewed as two steps. The first step is that they observe that there's a relationship between the joint probability matrix rank to the level of dependency among variables. So essentially, they are trying to use trying to manipulate the rank of a joint probability matrix to reflect the different level of the model dependency, variable dependency. And the second thing is that they are trying to utilize some standard matrix operators like SVD, singular value, eigenvalues, etc., to find such decomposition, so that then so that based on such factorization, the right-hand side estimator would compromise of several smaller matrices, and such smaller matrices only contains observed variables, and their value can be directly computed by counting in the original data. So that's basically the idea of spectral learning. And there's some challenges when we varies the number of hidden states and the number of observed states, especially when the number of hidden states is greater than number of observed states. We are going to introduce the feature vector to represent each observed variable instead of using the true value of the observed variable. So in that cases, it kind of increases the cardinality of the observed variable so that we are able to do the inverse operator. And overall, to regard the performance wise, it is able to overcome the local optima problem because it will no longer trying to estimate the values of the hidden variable h. They are only trying to dealing with all the computations directly with this x. And secondly, their speed is much faster. Okay, but one drawback is that as we talked about before, EM algorithm can be very easily applied to different latent variable models following some same fashion. But for the spectral learning, based on the different structures of different latent variable models, how to do the factorization will be quite different. And the way you do the factorization or the techniques you used in the linear algebra will be different. So that will be the main design for this spectral learning approach. Okay, so that's basically about the first part for today's reading group. Any questions before we move to the second part? Okay, so then the second part we are going to talk about is essentially about some parallelization tricks that aim to speed up the large-scale training for many of the recent learning problems. So let's look at firstly the motivation for like developing such metrics. So essentially the motivation for dealing with such a scalable algorithm is twofold. I think they are quite straightforward. So on the one hand, with the development of our technology, actually we're getting more and more data nowadays. So the data scale compared to maybe 10 years ago is has extended to very, very large like scales. So we have more and more data to deal with that will require a more scalable and more faster algorithm to deal with. And on the second perspective, we also, when we're building the model nowadays, we have more computation resources, computation power. So we are going to have building more and more deeper and gigantic models. For example, the previously when on the very beginning development of deep learning neural network, we can only do the learning over a very few layers of MLP. But now, if you look at all these very successful designs, the number of parameters is very large, right? So based on both the model size and both the data size, we need to call for some designs for some scalable algorithms. So, so in this lecture, they mainly introduce some parallelization strategies because we see that such urge is both due to the model size and also the data size. So such parallelization will be both developed in doing data parallelization and model parallelization. So for data parallelization, it's like, for example, we have different workers. Each worker can be like a computer that will construct a distributed system, or each worker can be a CPU on the same computer. We will talk about the differences between them. So for the data parallel, it's trying to see, okay, for the gigantic data set, we're trying to partition it to several different bunches to assign to different workers. And these different workers were going to use this different data block to do the updates for the model parameters. And for the model parallel, on the other hand, is that the model parameter is very large. So essentially, for each of these worker, we are only going to ask them to update a subset of these model parameters so that it can more quickly convergence. And in later on, the algorithm that we are talking about, actually, many of them can be viewed as both doing the data parallel and the model parallel so that they are becoming more efficient. So we are going to mainly talk about two types of algorithm with regard to their different parallelization. The first one is the stochastic gradient descent belongs to the optimization algorithms. So actually this lecture also provides some future reading for other optimization algorithms, but I think the overall key idea or the key design for the parallelization is quite similar. So if you are interested in, you can later on to look at the specific parallel design for other optimization algorithms. But overall, their key idea is relatively the same. So I just use this one as example. And the second one, I'm going to introduce the parallelization for MCMC algorithm. And I will take the example of LDA model where we have two algorithm, where the first one is called the graph lab LDA, and the second one is called the light LDA. So now let's first look at the parallelization for stochastic gradient descent. So before that, we just have a quick record of the algorithm of stochastic gradient descent itself. So for stochastic gradient descent, every time it will just randomly pick up a sample, one data point from the training data, and then it will try to update the parameters based on such single data point, right? And every time, every iteration, it will trying to randomly pick one iteratively to do the update. And later on, there are some mini batch version, which is trying to compute gradient based on multiple samples. So because update the gradients, especially for gigantic data set, if we want to compute the gradient for all these like billions of data points, it's very unrealistic. The speed will be super slow. So the idea is trying to just pick one data point to speed up, and the mini batch is just to pick a small set of data point to compute the average gradient. Okay, so let's look at how people are going to do the parallel for stochastic gradient descent. So the very naive one actually is proposed in like 2010. So it's called parallel SGD. So the idea is very simple. So essentially it will trying to partition the data to different workers, and all workers will update the full parameter until convergence on its own data split. So you can view that, okay, for each of these workers, they have different data, but on their own computer, they will have a copy of all the parameters for this model. And then they are going to only use their own data split to update the whole model parameters. And finally, after all the workers have convergence on their no-code data, the parameters, because if we have n workers, then we'll have n copies, then the final parameters for this model will just be the average of all these n copies, which is quite naive and intuitive. So you may think about some potential problem for this naive parallel stochastic gradient descent is that different workers may converge to different local optima based on the data subset that got, right? Because although we always assume that data is RID, but in reality, it is not the case. So essentially, by using each worker just to use different subdata to update the parameters, they may be convergence to different local optima. So therefore, the average cannot guarantee to be optimal. Because why this happens? Because all these workers, their communication only happens once. The first one is they get the data, and the second one is that they do the average. And among all the medium step, they do not have any communication with each other. So the first one is very naive. So that comes to the second approach, which is called hog-wide, and it is a log-free approach to parallel SGD. So the key idea they found is that so the key idea is trying to use is that it utilizes sparsity present in many problems. So let's see our optimization function has some type of structure where the objective function can be splitted into different objects called this sub E, where this E you can view it as an index for a subset of parameters. Here X is a parameter. So so this happens when naturally sparse data inside, for example, a linear regression. So let's say if I take random 1,000 examples out of my 1 million bigger examples, which is my total data set, I may find that instead of touching all the parameters, those 1,000 data that I picked up, they only touch 10% of the model parameters. Another example would be in recommendation system, where we usually represent users as a feature vector. For example, user A may subscribe contents like sports and user B may subscribe contents like music. But overall, these user vectors, they are all sparse vectors. And when we try to utilize them to calculate the loss, essentially the number of parameters they will touch is a very, very small portion. So so that's basically the intuition for us to design such parallel strategy. So here's a concrete example of the sparse SVM. So we have a concrete concept of what we refer to as sparse. So suppose our goal is to feed a support vector machine to some data pairs. So we see that it's, for example, Z1Y1 until ZEYE. And each of these Z is an n-dimensional input vector, and Y is a label for it. So we're trying to find the here X is the parameter. We're trying to find the X that maximize the hinge loss, that minimize the like the hinge loss plus the penalty. So if we know in prior that the examples Z alpha, that is each of these input feature vector are very sparse. So actually we can rewrite the cost function in the following form. So suppose we see that this E alpha are the components which are non-zero in Z alpha, meaning that, okay, if this Z alpha is an n-dimensional vector, but many of its entries is zero, so this E alpha are just those index which are not zero. And that's this DU denote the number of training examples which are non-zero in the component U. Here, this component U is each of the feature dimension for this feature vector. So in this way, we can actually rewrite it this loss function into this. Basically, the way we are going to do the revision is kind of the last part, right? Essentially, for the X we are touching, because this X will only be called when the corresponding Z's dimension is non-zero. So essentially, instead of looking at all the dimensions of this X, we're going to only interact with a subset of this subset of these parameters x. Okay, so in this way, each of these terms in this sum depends only on the components of x indexed by the subset E alpha, indexed by this U. So essentially, this is a semi-utilization as the example I just talked about, that if you think about that, when the data is relatively sparse, when we take a small portion out, then actually the loss, when we calculate the loss, it will only touch a very small percentage of the model parameters. So let's look how the Hawk-White algorithm is designed. So essentially, the idea is to, firstly, they were going to sample index set uniformly from all the parameters index. And then they kind of read the current parameter xe, and then evaluate the gradient of such function. And for each of these xe, because it's kind of it's kind of a bunch of parameters, but with different dimensions. But later on, what I'll do is trying to do the stochastic gradient descent for each of its coordinate. So let's see, we have 10 parameters like finance, sports, movie, and so on. I'm going to sample exactly one of them and perform stochastic gradient descent on just that parameter for a very small constant step. What happens is that if the data is sparse and if the number of parallel workers is not too big, then there's a high probability that the subset E sampled by different users are unlikely to collide with each other. And since the coordinates picked by each parallel workers do not collide with each other, there's no need to do complex synchronization. So we can think of that, okay, because the data is sparse, every worker, they are going to select only a small portion of these parameters to do the update. And if the worker number is small and the data is really sparse, the probability that they will choose the same parameter is very small. So in other words, at the same time, different workers are updating different parameters, so they will not affect each other at all. The only problem will happen is that if two workers, they are simultaneously update for the same parameters. So that's why we need the synchronization. But under this sparse data assumption, this probability is very, very small. So it's kind of a asynchronized approach. Okay, so that's basically the advantage of this algorithm. And it will perform excellent on single machine with multiple cores. So here we just view each of these cores like each CPU, GPU as a worker. But it will be less ideal for distributed setting where we have multiple machines. So in this setting, each different computer will be viewed as a worker. And this algorithm will not work that much on such distributed setting. And reason is that the delay among different machines, or in our case, the computers, requires explicit control. So now let's look at why it is the case. So the first potential problem is that if we're trying to view each worker as a computer, it may have this slower convergence. So let's think about it in this way. So in Hawk-White, every parallel worker is allowed to proceed at full speed. So they do not need to communicate with each other. As a sampled parameter set, E are very unlikely to collide with each other, right? However, in a distributed setting where we have delay among different machines, there is a theorem that given some type of objective functions and the step size, how would the delay affect the expected value loss function? So you see, and such effect is usually several orders of magnitude slower in communication. So essentially, you can understand it in this way because now the communication between the different computers, right, now becomes more expensive. It's like previously you are going to do a Zoom recording like us, together with all of you. So its communication is very convenient. But now, if now the worker becomes different computers, it's like you are trying to email, you are trying to send out a mail to a bunch of people, and such bunch of people is compared to the workers. So now the delay, the magnitude of delay will be increased very, very large. And because of the delay, so the process speed or the process progress of different worker or the computers will be very, very different. So essentially, maybe on one computer or one worker, for this bunch of data, it has already convergence, but for the other part of a worker, this one has not convergence yet. But due to such delay, there's a possibility that because now they are kind of not synchronized with each other, like we are doing in the room. Now we are just sending out mails. So essentially, it increased the probability that two workers will simultaneously update the same parameters. So that will cause the problem. This is one reason that it does not work very perfectly for this distributed setting. Okay. And the second thing is that uh, actually they are very alike. So delay also increase the variance of parameters. So by saying variance, I mean that if I took 10 different rounds of the algorithm and compare what the optimal or the final parameter value that I got, then with more delay, the parameters will become more and more spread out, meaning that, okay, the 10 results may be more different if the delay gets larger. That means you are less confident about your current estimation. So in the original paper, they kind of have these two elegant theorem to prove that. But on a high level idea is because that if you think about the uh, if you think about the delay by comparing that we are now communicating by sending emails. So essentially, although we are doing the optimization at our full speed, but the time window for different workers actually will be shifted. So it's kind of not synchronized. So it will cause some problem. Okay. Uh, so that's the second algorithm that we've talked about. And the third algorithm is called parallel SGD with key value stores. So this another approach. So the previous approach, we see that it relies on the assumption that the data or the algorithm or the cost function is very, very sparse. Another approach, which does not rely on the sparsity of the objective function of data, is to use this key value store, which is also known as the parameter server. The parameter server can be viewed as a central memory bank that every worker can talk with. So what the memory bank will do is to ensure that every worker has the same feature of parameters and integrating all the different messages from workers. So now every worker will not have their own local copy of the parameters, but all the up-to-date parameters are stored in this center bank. Okay, and so the role for this center memory bank is like if you are doing a project and within a group there's one people who is assigned to take the notes for the whole team. So the kind of the memory bank is the person who are taking the notes. It keep track of all the most state-of-art progress. And because now each worker will trying to send a request to the bank saying that, okay, I want to update these parameters, or just send a request to update these parameters, or send a request to say that I want to access these parameters. So this memory center back will kind of to do the synchronization. Otherwise, the parameters will not be the same for different workers to do the optimization. So there are several different synchronization approach in practice. For example, the bulk synchronous parallel, which is utilizing handloop, and some asynchronized parallel. But what we are going to discuss today here is called the stale synchronized parallel. It's kind of in between of synchronized parallel and asynchronized parallel. And we will see actually it's a very easy to understand algorithm. So it will give you a time window in terms of iteration. For example, let's see now we have a time window of size 3. Then the center back will keep track of the fastest and slowest parallel workers and guarantee that these two workers cannot be more than the window, meaning that their progress cannot be longer than 3 iterations. So for example, if worker 1 has already iterated 7 times, but worker 2 here have not finished its iteration for the 4th iteration, then the center back will just stop the first worker and ask you to wait for the second one. And the way it stops the first worker is that, as we see it now, the parameters are stored in the center back. And every time you want to do the iteration, it will send a request to the center back saying that, okay, can you give me the parameters? Or after the update, you will see send request to parameter saying, send request saying that, can I edit the parameter or update parameter? But now, because it is too fast, then the center back will just simply decline all of its requests. So the first walker, the quickest walker, fastest walker will just stop, and it will again trying to answer its request until this second worker reaches iteration 4, which says that they are within this limited time window. So that's essentially, you can see it allows such asynchronization, but such synchronization is bounded by such time window. So it's kind of one parallelization which is in between of synchronization and asynchronization. Okay. Okay, so that's basically about the parallel approach for stochastic gradient descent. We firstly talk about the first naive one, but it will have a problem that every worker will just result in its local optima. So when we take the average, it's very unlikely it will be the optimal. And the second approach take use of the sparsity of the data or the loss function itself, saying that, okay, when I take a small portion of examples out, it is of very small probability that each of these workers will select the parameters selected by these workers will collide with each other. So they will not. They are very likely not to collide with each other. So they can safely update on their own side and then integrate. And the third one is trying to construct such a central back, which will manually do the synchronization or communication between different workers. And the way to do the synchronization are 3 ways. The way to do the synchronization, to do the parallel 3 ways, either synchronize, asynchronize, or what we talked about previously, the still synchronize, which is in between the synchronized way and asynchronized way. Okay, so that's basically from the optimization algorithm perspective. And then let's look at the MCMC algorithm example in the LDA model, which we are all very familiar with. So the topic model LDA, to have a recall, is that there are 2 major matrices, which is a document topic matrix and the topic word matrix. So if we have a very, very large corpus, usually we have billions of documents as billions of words. So these matrices can be very, very large. And one traditional way to do that is to apply Markov chain Monte Carlo. But and we again, the very naive way to do the parallel is just a it's just like what we do in the naive parallel stochastic gradient descent. It's just ask each of these workers to run multiple chains in parallel and finally take the average or consensus between chains. And it will have the same problem as in the stochastic gradient descent, where that each worker will be tracked into its local optima. So essentially, when we take the average, it's very likely that we will not get the optimal solution. So there are 2 strategies towards how we are going to deal with this. The first one is called GraphLab LDA. So essentially, it will smartly partition the document topic and word topic matrices so that each worker will have a small portion of them, and this small portion of them will not overlap. And it's seemingly like a very similar idea in the Hawk-Wild algorithm, but the Hawk-Wild algorithm, to guarantee that they will collide, they will not do any more design just based on the data sparsity. But here, we no longer assume there's data sparsity. We will manually decide that, okay, such partition will not collide. So the so the way we are going to do that is trying to utilize the trying to form it as a graph partition problem. So essentially, we're trying to view this document and word as kind of the bipartite graph, and then we're going to find different graph partitions so that the overlap for different graph partitions are minimized. So that's essentially the key idea. And as we see, compared to the Hawk-Wild algorithm, the Hawk-Wild algorithm would utilize the sparsity of data. They will not run such graph partition algorithm. They can already have a high probability that each worker will not collide. But in this case, we will run this algorithm to get the assignment for each of these workers and then ask each of these workers to do the updates. So because it follows a similar value, each of these workers will attach a different set of parameters that will not collide. So it's again, like the Hawk-Wild parallel trick, it's asynchronized communication. And because each machine only needs to store these subsets of statistics with regard to this document and this corpus of words, so they will use less memory. Okay, but the drawback is that they need to convert the problem into a graph, and sometimes the graph can be very imbalanced. For example, by running the graph partition algorithm, sometimes the worker 1 will get a large number of documents and word pairs, but worker 2 will just get a small portion of them. So the running time for the algorithm will be bounded or limited by the workers with the heaviest workload, which is not what we want. So that's a potential problem for this algorithm. Second algorithm in this LDA is trying to use a different partition technique. So in this GraphLab LDA, we're going to do the partition by running the graph partition algorithm on the bipartite graph. But in this light LDA, what we're trying to do is to do the non-overlapping matrix partition. So suppose this is our word topic matrices. And for example, it's 3 by 3. So we have 3 words and 3 topics. Then the key idea is that, for example, we want to do the parameter updates by using 3 parallel workers. So the way we're going to do that is that, okay, at time step 1, I'm going to pick 3 non-overlap parameters to assign to each of these workers. For example, in this case, Z11, Z22, Z33. Why this? By saying non-overlap, I mean that all these three variables, their rows and their columns are both unique. So essentially, we know that if we pick the entries following the same columns, then if the row denotes the word and the column denotes the topic, then they will be all associated with the topic variable, right? But if we select them carefully, that each of them will have different rows and different columns, so they will not share any parameters. So we can safely assign it to different workers and then integrate them. But in the first iteration, we just update these 3 entrances. And in the second iteration, we select another 3 entrances that do not overlap each other. And in the third iteration, we'll select the remaining 3. And interestingly, once we do the selection like this, every time each of these 3 parallel workers will not affect each other, and the summation for all these shaded entries, if we integrate them together, we can see it will give us the original word topic matrices. So that's basically the key idea for this light LDA. So you see the key kind of differences between the GraphLab LDA is the way they do the partition. So for GraphLab LDA is trying to form it as a graph partition problem, but for the light LDA is trying to directly, for example, if you want to select such Z11, Z22, Z33, you only need to let such index to have some certain of constraints, and then you can do it very conveniently. So actually this is a method proposed by the speaker Yuan itself. So essentially it's published in 2050, and they have implemented a system which can actually achieve very efficient parallel for this LDA model. Okay, so that's basically the key idea for the second model, but in more details is that besides such solution, which I think is the most important part for the parallel trick, additionally for each of these worker, because they are going to have different bunch of data, and because the memory or the RAM of the worker is limited, they will further kind of split the data assigned to them into some data bugs, and they will process each of these data bugs sequentially. Okay, and so in this way, so in this way, they are going to kind of save many like memory usage, and the read and write for this small bulk of data between RAM and the disk the time consuming is not that much. Okay, so that's some additional tricks it used, but the key idea is that how they do this selection for these different workers. Okay, so yeah, that's basically all about the second topic. Basically, we can view that for this LDA model, both the light LDA and this graph LDA, they both kind of split the parameters itself and also split the data itself to different workers. And if we look at the designs for both the stochastic gradient descent algorithm and the MCMC algorithm, essentially the key idea is trying to avoid that parallel workers will simultaneously trying to update the same parameters, because that will cause some problem. So there's different way to deal with that. Utilize the data sparsity or utilize kind of a center bug, which serves as a control signal to different workers to communicate with each other. And finally, there's if the data itself is not that sparse, and we also do not want such center control, we will try to manually do such parameter splitting based on either graph partition or just like this non-overlapping metric partition approach. Okay, so yeah, I think that's all for our second half for this lecture. So any questions? Okay, then if not, I think maybe that's all for today's discussion. And if you have any questions afterwards or now, maybe we can discuss offline or now. And yeah, just feel free to let me know. And I'm happy to discuss with all of you.
Thank you.
Thank you,
Bye-bye.
Zijie.
Thank you. Bye.
Thank you. Bye.